Welcome back. We are pleased to have Lara, and she'll be continuing her second lecture on cluster algebra.
Thank you. Thank you very much. Yeah, so just to maybe remember what we did yesterday, we saw a bit of total positivity for 2 by n matrices or the Grassmannian to n, although I didn't mention that. And we took these patterns that we observed that from the triangulations that parameterize positivity test, we took that pattern and got to the definition of a cluster algebra. And then I told you, yeah, mostly about how they are defined, how we generalize the combinatorics of n-gon and flips inside the triangulations of n-gons to quivers and quiver mutation. And then we saw how to associate just a tuple of variables, some algebraic layer to this combinatorial data, and how that would mutate, and how we get to the definition of a seed mutation, and then a cluster algebra as being generated by all these collections of variables that we get by running through the mutation rule. And the last thing I mentioned was the notion of a restricted seed, and it was a bit rushed yesterday, so I want to repeat that and then tell you how to get to subcluster algebras using this notion. Oh, and then for the rest of today, we will see some general results about cluster algebras, some structures, and then move on to a geometric interpretation called cluster varieties. And that would lead us kind of naturally to the notion of tropicalization of these spaces. We go a bit outside of the algebra bubble. But let's first stick in the setting of yesterday. So if we have a seed, and from this seed, I want to get to another seed by doing something on the quiver, reducing its number of vertices in order to get to something that would generate me a cluster algebra that is also a subalgebra of the algebra of this guy. And for that, I can do two things. And I take another seed Q prime. And I want this one to be obtained from Q. In one of the two following ways. The first one is, and by either, the first one is I just freeze some vertices in Q, and then I have more frozen variables than before. Just freezing some vertices in Q. Or the other is by partitioning the vertex set in Q in two parts so that there's no arrows from the second part of my vertex set to mutable vertices of the first part. So this is taking a partition Ij of Q0, the vertices of Q, such that there don't exist arrows in Q from mutable vertices in I to any vertices in J. And then Q prime is the full subquiver of Q with vertex sets of Q0 prime equal to I. Okay, so let's do an example of what this means. Oh, and then I didn't say what this, let's see what came from. So Q prime is a seed, or this seed with Q prime is obtained from Q in either of these ways. And then we call S prime, then S prime is a restricted field of S. Okay, so let's first just focus on the quiver part and take Q just to be this A3 quiver. So the first option is just freezing some vertices. So we could define Q prime just as this quiver, freezing the vertex 2. And then whatever variables I associate to Q, if I stick with the same variables in Q prime, that is a restricted field. And then when I'm at Q prime, I have a frozen vertex in the middle, so I can also do a partitioning that would satisfy this definition. And that could be, for example, just sticking with the vertices 1 and 2. So let's check if I is 1 and 2. And J is just 3. Then in Q prime, I don't have any arrows from mutable vertices in I, 1, to any vertex in J, 3. So Q double prime could be just 1, 2. And again, if I attach variables to Q prime and keep the same variables for Q double prime, then this is also a restricted field. And this notion is interesting because of the following proposition. So if I now start with my cluster algebra generated by the seed S, then the cluster algebra generated by a seed S prime that is restricted is a subalgebra, because by this definition, all the cluster variables I generate for the restricted seed are also cluster variables in the original seed or in the original seed pattern. So it is contained naturally, but it is also a subalgebra because I have less cluster variables. So we're in the same ambient field. We're generating an algebra that has a subset. The generators of my restricted seed cluster algebra are a subset of the generators of the original one. So if S prime is a restricted seed, of S, then the cluster algebra associated to S prime is a subalgebra, a subcluster algebra. And maybe I should call this also a definition, because that would be my definition of what a subcluster algebra is. It's a subalgebra that has a cluster structure that is compatible. Good. So, yeah, any questions on that? Mm-hmm. Reducing the number of mutation steps? No. So that would maybe more correspond to taking a quotient, or if you fold, then you have phenomena like that. In this case, it's more like if any mutation here, if you would draw the whole, like this diagram, the whole pattern, any mutation here has an associated mutation here, but up here I have more mutation. Mm-hmm. Yes. Yes. Yeah. Yeah. So subalgebra really means that you have a smaller pattern. So, for example, if I would draw this kind of diagram for this algebra, for the A3 cluster algebra, Well, I mean, in this case, it's also an isocahedron. It would look something like this. And this one is one edge on the back. So every vertex here is a seed for this 1, 2, 3 quiver, and edges are mutations between them. If I would now go to, maybe let's do another one. Let's say this one is 1, 2, 3. And let's just consider freezing 3. This would correspond to one of those pentagon faces. So I would have the same seed. So all the seeds that are corresponding to this pentagon are seeds for my subcluster algebra. All the mutations here are also mutations up here, but there are mutations that simply lie out of the cluster pattern for this. Right, right. It's, you always restrict to some phase of the polygon. Okay. Right. So I think that was all that was left from yesterday. Yeah, exactly. So the part that I would prove here is that yeah, like exactly that statement. So that every mutation here corresponds to a mutation up here. And then we could also add a statement about the cluster variables, like all cluster variables here are also cluster variables here. Okay. Yes. Good. So then, right. So I put the example from yesterday back on the board because I wanted to make some observations in this example and then tell you which of these observations hold more generally or in which generality. And the first one is just looking at the types of expressions that I get for all the cluster variables. So we live here in this field of rational functions, x1, x2, and our mutation rule always divides by a variable. We've already seen in this step that we have to divide by a rather complicated expression. And it is kind of surprising that we end up again with a Laurent monomial. So in the denominator here, we always just have variables or monomials appearing. Although on the way, we divide it by quite arbitrary rational functions. So this statement holds more generally, and it's called the Laurent phenomenon. And that is when I take a cluster variable of any seed, it is always a Laurent polynomial in the variables of my initial seed. So remember, cluster was the term just referring to the variables, the tuple of variables in the seed. So every cluster variable is a Laurent polynomial in the initial cluster. And that's, so if I write x for my cluster variable, that means x is in the Laurent polynomial ring. Let's say more precisely, I have the following statement where x1 to xn are my mutable variables, and xn plus 1 to xn plus m. I slightly changed notation from yesterday because there was so many typos in the note. This convention won. So these are the mutable vertices, mutable variables, and these are the frozen variables. And this observation about the frozen variables is not visible in our example because we didn't have any frozen variables. But in fact, I will only have mutable variables appearing in the denominator of these expressions. So if we go to this example, then we could, of course, be a bit more specific. First of all, okay, yeah, all the coefficients are integer, but in this example, they're also all positive. We only have plus signs appearing in the expressions. And this is something that you can observe in any other example, and Fomin and Zelevinsky also did that. And they formulated the conjecture that, in fact, the coefficients are only natural numbers. So, and this observation, especially when you think about our motivation from total positivity, is pretty crucial. Like, this would not be any use in total positivity if we actually have negative coefficients appearing in these expressions. So this conjecture is called the positivity conjecture of the law phenomenon. And I would just add here positive. And I will add here natural numbers. So this was a conjecture in Fomin and Zelevinsky, and it took several years to confirm this conjecture. For our context right now, with Q being a quiver and the cluster algebra associated quiver, this positivity conjecture was proven by Lee and Schiffler. And then there's a slight generalization of cluster algebra. So we no longer take a cluster algebra associated to a quiver, but to a skew symmetrizable matrix. The idea is that a quiver gives us a skew symmetric matrix, it's incidence matrix, but we can slightly generalize that concept and still attach a cluster algebra. And in this more general context, it was also proven a few years later. So maybe I should put some years. I think Fomin and Zelevinsky, this was the first paper in 2003. Lee Schiffler was 2006, or yeah, 2006. And then the most general version, or let's say all generality, was proven in 2014 by Gross-Hecking, Kiel, and Kansic. And the interesting thing about this paper is that it's no longer algebraic. So in Lee and Schiffler and Fomin Zelevinsky, these papers are pretty algebraic. So Lee and Schiffler, I think they used representation theory to prove this result. But this paper suddenly switched gears and goes to algebraic geometry, birational geometry, attaching spaces to cluster algebras, and then having certain counting problems on these spaces that realize the coefficients appearing. And this is the way they prove the conjecture. So I really like this kind of relation between the algebraic side of cluster algebras and then the algebraic, the varieties associated. I was pretty impressed when this paper came out. So I was very curious to learn this. So in a bit later today, I will tell you a bit about the geometric side of cluster algebras and what are the spaces you can associate to them. That eventually, yeah, led to the proof in all generality. Any questions on this? Okay. So then let's do one more observation here. And that's the fact that the system is periodic. Like after these 5 mutations, we ended up with a seed that is isomorphic up to like a permutation of the vertices to the one we started with. And this phenomenon that we only have a finite number of seeds in our pattern is called finite type. So cluster algebras with only a finite number of seeds are called finite type. Let's put this as a definition. So if it has only a finite number of seeds, it also only has a finite number of cluster variables. And we get a pattern like on the other side of the board. And Fomin and Zelevinsky wrote a second paper on this. I mean, they wrote 4 in total, but the second paper they wrote on cluster algebras contains the finite type classification. And that's the following. So a cluster algebra AQ is of finite type. If and only if. And we're going to do the following here. We're going to first restrict our attention only to the mutable part of the quiver, which is the one determining the pattern. And it is of finite type if and only if in the mutation class of this quiver, at some point I will find a quiver that is an orientation of an ADE Dinkin diagram. Yeah, so yesterday I didn't mention it, but we saw it in Sajid's lecture that in fact the cluster algebra only depends on the mutation class of its quiver. This is a result that Fomin and Zelevinsky showed. So it doesn't really matter if I have this pattern over there. It doesn't matter which seed I choose to start to generate my cluster algebra. And it also doesn't matter what are the variables associated with it, because there will always be algebraically independent in some ambient field. So the cluster algebra, the important information for me is really just the mutation class of this quiver. And then moreover, to determine if the cluster algebra is of finite type or not, if there's a finite number of seeds or not, I only restrict my attention to the mutable part of Q, and then I can check if somewhere I will find an orientation of an ADE Dinkin. Well, the recipe would be that, like, look at the mutable part of Q. You can forget all the frozen variables and start mutating and see. No, I mean, yeah, by now the quivers that appear very well understood. So by now there's like lists of what kind of quivers are finite type, even if they don't look like it. Like, for example, this is one that is obtained from one mutation of the orientation of an AD, or like this one, maybe, oh no, I'm not sure if maybe some orientation of the arrows is bad. In the notes, there's an example. Okay, this is of type D4 or something similar. Yeah. Mm-hmm. The skew symmetrizable ones, I mean, the more, yeah, it's also known for those. And in that case, it also goes through Dinkin diagrams. So there's a way to a skew symmetric matrix to associate a Cartan matrix, a Cartan component, Cartan companion. If you're in ADE type, it will really just be this Cartan matrix. And when this Cartan companion looks like like the Cartan matrix of a Dinkin diagram, including the other finite types, exceptional types, then it's finite type. So just extend this result by the other Dinkin types. Yes, skew symmetrizable matrices. Yeah, when the matrix is skew symmetric, you can always associate a quiver. Like one example of skew symmetrizable would be something like this. It's not skew symmetric, but you can find some diagonal matrix, multiply this matrix with that, and it will be skew symmetric. So that's the notion of skew symmetrizable that is used. Yeah. Okay. Yes. Yeah, it is. It is indeed. I mean, I think this is the entry ticket of cluster algebras to the heart of pure mathematics, essentially. And this has stimulated a lot of research. And there is like a bunch of relations. When something is classified by Lincoln diagrams, many of those objects are related to cluster algebras. I mean, one example is representation theory, of course, and flag varieties and all these objects. And another relation is also singularity theory. You have like these dual singularities that have desingularizations, and these Lincoln diagrams appear, and there's cluster algebras that are associated to them. So there's really a big zoo of applications coming out of this observation. Okay. So before going all in on cluster varieties, I wanted to make one more observation about this cluster algebra associated to a triangulation of an n-gon. So yesterday we saw that if T is a triangulation of an n-gon, that we could associate to that a seed where Qt was the quiver obtained by vertices corresponding to edges of the triangulation, and then in every triangle of the triangulation having an oriented triangle in the quiver, and xt was the tuple of Fluker coordinates with indices the endpoint of the edges. So if I take the cluster algebra associated to this quiver, or the seed, and I tensor it with the complex numbers, then this is isomorphic to one of the Fluker algebras we've seen in the morning, or the homogeneous coordinate ring of the Grassmannian n. So we looked at triangulations from the point of view of 2 by n matrices, but if these 2 by n matrices satisfy the full rank condition, that their rank is 2, then they represent elements of the Grassmannian. So this is kind of the step from the matrices to the Grassmannian. And we get an isomorphism of the homogeneous coordinate ring of the Grassmannian in its Fluker embedding, or the Fluker algebra, and this cluster algebra associated to a triangulation. And this theorem appears in Fomin and Zelevinsky's first paper, and Jean generalized it to other Grassmannians. So let me state this here, maybe. So for any Grassmannian, any Fluker algebra of a Grassmannian, there exists a cluster algebra satisfying an isomorphism of this form. This I'm already kind of getting into geometry jargon, where I don't really mention isomorphisms anymore, but just identify things. So this is a cluster algebra. What I mean is there exists an isomorphism of this form. And then, no, I will list now the observations of when this is finite type. So the only finite type Grassmannians are the following. And I assume here that k is less or equal to n, and that's double the notation. Well, the Grassmannian 2n is this example. The triangulation is of cluster type A. So you can always find like a triangulation that has all edges getting out of the same vertex, and then the quiver associated, its mutable part would just be a chain like this. So this is a type A cluster algebra. Then I have the Grassmannian 3,6, which is of type B4. Grassmannian 3,7 of type B6. And Grassmannian 3,8 of type E8. So these types, you can see the dimension or the index of these Lincoln diagrams is lower than the dimension of the Grassmannian, but this is because I am only considering the mutable part of the quiver. Okay? So the number of vertices of the quiver here that I need to generate this cluster algebra is the dimension of the Grassmannian plus 1. And this is just the number of mutable vertices in each of those quivers. Okay. Yeah. Yeah. Right. Yeah. So I mean, this theorem follows the construction of Jean, and like she gives one construction for each Grassmannian and one initial quiver, and this initial quiver follows this classification. There's other ways to associate cluster structures to this algebra that are non-isomorphic of different cluster type. The only one I actually know is this one. It also has an A4 cluster structure. This is alternative construction. But yeah, so this theorem talks about this one cluster structure associated in that paper. I don't know of any. Like, I think there's not enough research been done on this kind of how many different cluster structures or what. Yeah. Yes. Yeah. Okay. You know what? Let me adjust this also and say has a cluster structure. Now that we're getting so precise, because this is the conceptually this is the better way to think about it. Like, what do I need to do to show a cluster, an algebra has a cluster structure? Well, I have to find some C, generate a cluster algebra, and show there's an isomorphism. But it is true that we have these examples, for example, here of the two alternative ways to show that this is a cluster algebra, and we get to two different cluster structures. Right. Right. Hmm. Yeah, I haven't checked that, but that's very interesting. So this A4 type comes from a flag variety, I think 2, 4, 5. And the affine cones are isomorphic. And the standard construction of cluster structure here would be A4, and then the affine cones are isomorphic, so the algebras are isomorphic. But no, I think yes, you're right, because here I have different cluster variables. Oh, that's interesting. Okay. Maybe later I do that example. And I don't know any example of that. It is possible. I mean, the question if a cluster algebra is finitely generated, or like if it has a finite presentation, is another one. And then in principle, it could happen. I don't know any example, but I also don't know a result that says this is not possible. Mm-hmm. Yeah. There's not finitely many. Yeah. The basis is infinite. Just, yeah, how you write it down has kind of a finite touch to it. Yeah. Okay. So, let's see. I think I'm doing terrible on time, probably, but that's okay. So I still want to get to cluster varieties. And this theory has been kind of developed by Fock and Goncharov pretty soon after the introduction of cluster algebras. And the idea is, instead of constructing an algebra, I want to construct a space. I have a cluster pattern, and instead of going into the algebra direction, I want to go into the geometry direction. And what I do for that is I don't associate a tuple of variables in some field, but I associate an algebraic torus to every field. And this is just, so it's an algebraic torus, a C star to the n plus m, my number of mutable plus frozen vertices. And it comes endowed with a basis, or like with a set of coordinates that I call cluster coordinates. And these cluster coordinates are exactly the cluster variables I have in my field. And then I can define the A cluster variety. No, sorry, I'm going ahead of myself. So if this is an algebraic torus, and these are my cluster coordinates, then the mutation rule that we've seen that changes the cluster from one to the other, I can interpret it as a map between two algebraic tori associated to two different fields. And it's a local change of coordinates from going from one torus to the other. So I have these mutation maps. So if I have S and S prime, two seeds related by mutation in direction K, then the mutation induces a map, mu S S prime. It's a birational map from the torus, the C torus TS to the C torus TS prime. And it's given by the following. So if I take a point T1 to Tn plus m in my torus TS, I will send this to the following. So the first k minus 1 coordinates, I just keep them as they are. And then in the kth entry, I just place my mutation rule. And the rest, I keep them the same. So this is a birational map. Let's check why. I want to land again in an algebraic torus, meaning that all these entries should be non-zero complex numbers. And there is some possibility for this entry to become 0. So that is exactly the locus here where my map is not defined. So it's not a morphism, it's just a birational map. For that reason, it is birational because I can write down the inverse. We saw already that mutation is an involution, and that is the idea of how to see that is birational. And with these maps that I call them, I don't have a name, maybe transition function. Associated to a seed S is, and now I think I've been using the calligraphic A also for the cluster algebra, right? Let me change that to just normal A. And now the calligraphic one would be my cluster variety. So what do I do here? Well, I run over all the possible seeds I get from my seed S. So I take S prime, mutation equivalent to S. And for every such seed S prime, I have a torus, C star to the n plus m with its coordinates. And I glue these along the biggest possible locus that these maps dictate. So we have already established these maps are not isomorphisms. This entry here gives me a locus where it is not defined. The inverse will also give me a locus where the map is not defined. And I glue two tori along the biggest open locus where this map is defined. Okay. And we're going to take the cluster structure of the Grassmannian 2-4. So this was from the triangulations, just a quadrilateral and its two triangulations. So consider, and we're going to do the affine cone of the Grassmannian. So its cluster structure was given by these two triangulations. And the cluster variety I will associate is now two copies of a torus, C star to the 5. The number of edges here is 5. And really what changes between these two tori is just the set of coordinates that I associate. No, this is infinite. This can be an infinite atlas, or yeah, the seeds can be an infinite number. Mm-hmm. Yes. In fact, already, it is infinite in infinite type. But already here, what is a bit hidden is that if I define a scheme, I need to have a transition maps between any two open sets, right? And I told you only the transition maps between two that are adjacent seed tori. So in this definition kind of behind, I have to consider all the sequences of mutations that would connect any two different seed tori, and consider those maps as well. Yeah, so it gets a bit abstract in infinite type. In this example, it is more tractable. So the A cluster variety here would be the union of these two tori. And the gluing is given by our transition map. That corresponds to the flip of the two triangulations. And this is an example of a cluster variety with the definition of Fock and Gontran. There's a bit of there's no consensus in the literature of what actually is a cluster variety. So if you read a paper, you have to be careful and check the definition. This is the one that Fock and Gontran give, and I like it because it is kind of the more structural, let's say. An alternative is to just take the spectrum of a cluster algebra, and in some parts of the literature, the spectrum of a cluster algebra will be called a cluster variety, and that is an affine compactification, or like an affinization of this one. Yeah. Okay. Any questions? Yes. I will get there. Not integers, but yes. Yeah. Right, exactly. So now we have, this is an excellent point, right? If we go to our transition functions, we can make the same observation that we did in the seed pattern. There's only positive signs here. And we even know the positivity conjecture that tells us even in all the compositions of these functions, there will only be positive signs. And Fock and Gontran made this observation and said, okay, well, so we don't need subtraction, which actually means not only can we go to integers, we can go and work over any semi-field. And that leads us to the notion of tropicalization. Thank you. It was a perfect question for me. Yeah, I mean, that's certainly something you can do with cluster variety. And there's some results in the literature around that. Yeah. So I would say it kind of opens up new research questions. I don't know if there is a strong application of, okay, I don't know, some finite field points of this cluster variety are this thing. But yeah, certainly possible to investigate these questions. So yeah, so let's continue with this observation. The transition functions are subtraction free. Which enables us to work over semifields. So just to recall, P is a semifield. If P has an addition, let's write this. And multiplication. Addition is commutative and associative. And multiplication is such that P becomes an abelian group. And then we have the compatibility. A plus B times C is AC plus BC. Okay, so what are examples of semifields that are interesting? Well, if we think of total positivity, certainly the real numbers, the positive real numbers. So everything that is missing here, if we think about a field versus a semi-field, is the inverses of the addition, meaning we cannot subtract. So we don't need to subtract. Certainly the positive real numbers are a candidate. But then there's other interesting semi-fields, like the integer tropical semi-field or the tropical semi-field. And in this, we consider the operation taking the maximum as addition and the sum as multiplication. And this also satisfies the axioms of a semi-field. And this is the field that leads us to the tropicalization of cluster varieties. Let me pause a second, and I think the last thing I will do is define the tropicalization in this sense. So this is another semi-field. As I said, it is all integers. The addition, the semi-field addition, is given by taking the maximum of 2. And the multiplication in the semi-field is given by the usual addition. So the maximum does not have an inverse. It is not a field, but it satisfies commutativity, associativity, compatibility, and integers with additions. Okay, so this leads, or let's just work with this semi-field for a second, and I will tell you a few things of what happens if we take a cluster algebra with respect to the semi-field. So if we take now a seed torus and its integer tropical points, that's what I will call the points of this torus when working over this semi-field. So this is called the integer tropical points. This can be identified with the co-character lattice of my torus tensor with these semi-fields. So as a reminder, the NS is the co-character lattice. That means I can get my torus by taking this lattice and tensoring it with C star. Now, if I keep working over these over the tropical semi-field, I can also check what happens to my transition functions. Yeah, so this is a lattice. So I have an action on Z on the lattice. But as a tropic, if I change the structure here, I actually lose a bit of that structure because ZT does not have a multiplication. So here I can multiply by integers and I keep staying in the same field, and I can take addition, like I can add points and I stay in the lattice. And here I lose the addition. So this is no longer a Z module, but is a Z torsor, where I can take multiples of points, but I can no longer add points. So this is the structure that I lose when I go to integers. As I said, they're the same thing, just I cannot add anymore. Okay. Let me just write the transition functions on the board as the last thing. So if I work over a semi-field, I'm just doing exactly the same thing I did before, just that my operations of multiplication and addition are no longer the classical operations. So really, if I want to know the transition functions over the semi-field, all I have to do is I go back to my original transition function formula and replace all the pluses with maximum and all the multiplication with pluses. And I'm going to save time and just do it here. So maybe not actually. Maybe not. It's going the Booleans are also a semi-field, I think. So you could, yeah, it is certainly of a similar flavor where I kind of get rid of structure that I don't need. And the Booleans is like an extreme case. And yeah, I'm somewhere in between. So let me write this down. So if I have a point in my tropical integer points of a torus, remember I can identify them with a lattice point. So this is some lattice point. I send this to the following. As before, I keep, so the assumption is the same. S and S prime are two seeds related by mutation in direction K. So I keep all the entries that are not in the K position. These are integers, yeah. So this is in this part, and I will always think about this now. Well, this I will think about it as a lattice. I can identify it as sets. I can identify them. And here I now take the minus AK, which corresponds to dividing by TK, and I add the maximum, which corresponds to the sum of the two monomials. And for each monomial, I will have the sum of the exponents, if you want. So here I have the sum over all the IA, where I corresponds to where there is an arrow from I to K in my quiver. And I have a sum over all the arrows from K to J, AJ. And I consider the maximum of these two expressions, and the rest of my points stays the same. So maybe one last observation. When we define the cluster variety here, we have to be careful where this map is defined, right? And there was this locus where it's not defined, where we cannot take the image of a point because we would not land in the torus. So this does not happen here, right? I'm just taking a lattice point, and this is a piecewise linear map. In my space, in the lattice, I have one hyperplane that separates the two sides. And they depend on whether this term wins or this term wins in the expression. But this is certainly defined everywhere in the lattice. So in this case, transition functions are bijection. And the cluster algebra will just be copying that definition, take a lattice in this sense for every seed, and identify points into lattices if they are images, one of the other, with one of those. And I will continue there. Thanks.
Questions?
So I think the deep locus, if I remember correctly, is you take the spectrum of the cluster algebra on the one side, and you take this union of cluster tori on the other, and you ask for their difference. And sometimes the cluster tori cover everything, and sometimes they don't. I think, no, from the definition, I would say you only see that this could happen. But then sometimes it does not happen. Sometimes they actually coincide, and we have an atlas. But yeah. Right, so maybe this was not so clear here. So this is by construction a subset of the Grassmannian, or the affine cone of the Grassmannian. They are not the same, right? Because already, like in the Grassmannian, I can have certain points where Plücker coordinates vanish. And here, this is not allowed. Like all my Plücker coordinates are C stars. So yeah, so I certainly get a difference. And there's a whole theory of compactifying cluster varieties and how to do that in a sensible way to get to the Grassmannian or other spaces. But that's like, for now, I'm just working with this open part, this union of cluster tori.
Any more questions? If not, let's thank the speaker again.